Does it sound okay? Much better. Okay, sorting out all this technology takes time. Alrighty, I'd like to begin this talk with a digression. We had to fiddle with the technology because these slides have a strange aspect ratio. If my slides are 4:3 but the projector is 16:9, I waste 25% of the screen. If my slides are 16:9 but the projector is 4:3, I waste 25%. So these slides are actually 20:13. And our technician seems to have made them very nicely match the screen. I think it looks pretty good. So a hand for the audio guy, the video guy. The optimal compromise ratio is 8:3√3, and if you take the continued fraction and then truncate it, you get nice integer ratios. 20:13 is accurate within 1%, and it wastes less than 13.5% of the screen, whichever projector you run up against. Okay, but I'm really here to talk about the most popular programming language in computer science. The most popular programming language in computer science has no interpreter or compiler. Its definition is not written down in any one place. It's changed a lot over the decades, and those changes have introduced some ambiguities and inconsistencies. We're going to take a look at that. Today, dozens of variations are in use, and the complexity of this language has reached the point where it needs to be re-explained, at least in part, every time it's used, but unfortunately, it usually isn't. Much effort has been spent in hand translating between this language and other languages that have compilers. I've done this myself. I spent many hours on that. The language is quite amenable to parallel computation, but this fact has largely gone unexploited. Many people have shaped this language, but it was not a design by committee. And here on this slide, I've got a few of the early contributors, Gerhard Gentzen, John Backus, Peter Nauer, and Alonzo Church. But dozens of others have contributed to the development of this language also, and they are largely unheralded. It's hard to search on the internet for examples of this language because today's OCR and PDF technology fails to capture the most salient syntactic characteristics of the language. And I would tell you the name of the language, but it doesn't seem to have one. So for the purposes of this talk, I'm going to call it computer science metanotation. This programming language has a number of built-in data types you can take for granted, the usual Boolean, integer, real, maybe complex numbers, such lists and arrays. It also has user-declared data types, which you can regard as records or abstract data types or symbolic expressions. These are defined by BNF notation. The code is in the form of inference rules. Conditionals can be expressed in several ways, but the primary one is rule dispatch through non-deterministic pattern matching. And recently has developed some very interesting repetition notations, overlines or ellipsis notations, and sometimes iterators. Its primitive expressions are drawn from logic and mathematics, and it's kind of open-ended. And there's this very interesting and distinctive special operation, capture-free substitution within a symbolic expression. So here's an example of a data declarations in this language. This should look very familiar to you if you've read any SIGPLAN papers. We're going to take a much closer look at this slide later, so I'm going to skip over it now. Here's some examples of code. This is non-deterministic code. This is taken from a 2014 POPL paper. The authors of this code very kindly provided a signature declaration at the top in a box. This is optional, not all authors do this. It defines a little function called no conflict, and there's even a comment. Ooh, check for equation conflicts. And there are two different ways this is implemented, and you can choose either one non-deterministically, whichever one works. If you want to prove no conflict, you can use the first rule or the second rule. These rules happen to be given names. And all you have to do is prove the premises in order to prove the conclusion. And I have highlighted here in very light blue a very interesting feature of this code, that it uses overlines, and in fact nested overlines, to indicate various kinds of repetition. We'll look at that more closely later. Here's a different example of code from another paper. This is from POPL 2016. And this code is part of a type checking algorithm, and its structures look fairly familiar if you take the time to look at it. I'm not going to give you much time to look at it. Instead, I want to draw your attention to the fact that in each rule, by convention, you can view the part before the colon as an input expression, and the part after the colon is an output type that is being calculated. And with this convention, execution of the code looks very much like the execution of a Prolog program, except that nowadays we know much more efficient methods for searching the solution space than using a strict deterministic depth-first chronological backtracking algorithm. We have better ways of solving these systems of constraints now. So we can view those as inputs and outputs. Another feature of this code I will draw your attention to in the middle rule is that the ellipsis, that's the technical name for the 3 dots. The 3 dots are used in 2 different ways in this code. In the consequent on the bottom is used to indicate that any number of m's can appear. And in fact, the number of m's should equal the arity of op. That's expressed through the AR function. Up top, we have an iterator. The 3 dots indicate an integer range. That integer range, in turn, is being used to drive the indication that the premise to its left actually appears a number of times, once for each value of I. So there's metanotation within metanotation. This is all very interesting. Okay, so I think I've demonstrated this is a programming language. I've written type-checking algorithms in this language, and I've hand-translated them to Java and Scala in order to get them to work. But now I need to support my claim that this is the most popular language in computer science. So to do this, I did an analysis of some conference papers. I looked at every page of every paper of every POPL conference from 1973 to 2016. That was 1,401 papers, about 17,000 pages of material. Yes, I eyeballed every page. I was looking for uses of the inference notation, of repetition notations, and of substitution. This summarizes the results for the use of inference rules. I've aggregated the data into 5-year intervals going backwards. So each bar represents 5 years worth of conference papers. The total height of the bar indicates the number of conference papers, and the light part of the bar at the bottom indicates the number of papers that were using inference rules. And as you can see, for the last almost 25 years, over half of all POPL papers have used computer science metanotation. And I dare say that no other programming language can make that claim. Then to double check this, I looked at just the last 3 years of PLDI, UPSLA, and ICFP, and the last 6 years of PPoPP. And I went 6 years on PPoPP because I wasn't finding very much. I'm going to talk about that. For the last 3 years, over 1/3 of all PLDI papers were using this notation, over 1/3 of UPSLA papers, almost 2/3 of ICFP papers, and about 5% of PPoPP papers. And so I spent some time studying those papers and thinking about it, and I realized that of all of the major SIGPLAN conferences, PPoPP, relative to the others, tends to focus more on what's happening at runtime than what's happening at compile time. In PPoPP papers, you'll find these fantastic geometric diagrams describing memory layouts and data structures and threads and things like that. You'll find all these wonderful charts showing measurements of runtimes. But there's a little less emphasis on describing compilers and type systems, which is where this notation primarily tends to get used, although not exclusively. It's used for other purposes as well. Okay, so in all, I've studied about 25,000 pages of material. I think I've supported my claim. This is a very popular notation, and I claim it's a programming language. So here's the structure of this talk. We're going to examine the history and variety of 5 aspects of this notation, identify some problems that have arisen with substitution, overline, and ellipsis, and I'm going to propose some possible solutions. And I want to discuss just a very little bit how we might formalize this language with the goal of eventually mechanizing it and actually giving it a compiler, an interpreter, and tools. So first, let's talk about inference rules. Okay, in 1935, Gerhard Gentzen published a paper on the subject of natural deduction, and he creates this rule notation where you write a bunch of premises above a line and then a conclusion below the line. And you can see that in the center of the middle box there. The top box is just the title of the paper. And then he uses this to develop his logic. And down at the bottom, you can see very familiar rules, although written in this German script. So if you know A and B, then you conclude A and B. If you know A and B, you can conclude either A or B. And if you know either A or B, you can conclude A or B. And that's the gist of those particular 5 rules of natural deduction down there. This is 1935. Today's computer science inference rule notation extends this only a little bit. One is that we've introduced the habit of having many, many premises in our rules sometimes, if our algorithm is very complicated. And so instead of stringing out premises horizontally, we also stack them vertically. We cram in as much stuff as we can above the line. The other thing I noticed, there was a huge variation in the format of the labels. Sometimes the label's on the right, sometimes on the left, top center, top right, lower right, wherever you want. It might be right adjacent rule, it might be stuck out in the margin, it might be capitalized, title caps, all caps, small caps. Some labels are alphanumeric, some have mathematical symbols. They come in all sizes and styles of fonts. If it's a multi-word label, the words might be separated by spaces or hyphens or periods, or might be camel case. And the enclosers, there might be parentheses around the rule name or brackets or angle brackets or nothing. I've seen nearly all these variations. And all these variations really aren't a problem. It seems to be a great way for authors to have stylistic self-expression, and it's relatively harmless. You can usually figure out that something is a label and not a premise, provided it's not top center and looks too much like a premise. You have to watch out for that. Okay, wide variation, not a problem. This is sort of typical when a language is used informally. Okay, that's about what there is for inference rules. That notation has been fairly stable over history. Now let's talk about BNF. Okay, historical background on grammars. In about the 5th century BCE, give or take a century, Panini wrote a Sanskrit grammar that contained numerous concise technical rules that described Sanskrit morphology. This is a marvelous technical work. It contained rules that, if you transliterate the notation into modern notation, look very much like BNF. I just put up this example because sometimes it's forgotten in the West, and this shows that the study of grammars really has a long historical background. In the 20th century, Axel Tude studied string rewriting systems defined by rewrite rules in 1914. Not long after that, Emil Post studied tag systems, in which symbols were repeatedly replaced by strings and studied what, when I was in college, were called post-productions. Although he did this work in the 1920s, it was not published until 1943. In 1947, Andrei Markov and Emil Post independently proved a very interesting theorem, which is the word problem for semigroups, which is a problem that's been posed by Tude, is undecidable. And this immediately interacted with undecidability results coming from Church and Turing at about the same time. In 1956, Noam Chomsky published 3 models for the description of language, which described grammars with production rules and what we now call the Chomskyan hierarchy of grammars, which at the bottom has the so-called type 3 and type 2 grammars corresponding to regular expressions and context-free grammars. So you'd think that BNF and regular expressions would have a very closely involved history. Turns out that they developed almost independently. So let's take a quick look at regular expressions, because they will figure into our story. Regular expressions actually developed out of trying to understand neural networks. An early version of neural networks by McCulloch-Pitts were discrete nerve nets, and in 1951, Stephen Claney developed regular expressions to try to describe the states of these nerve nets. He used a wedge symbol for choice, and he considered using a postfix unary Claney star of the kind we're used to, but he decided to make it a binary operator so that his notation would avoid generating empty strings, which kind of mucked up his formalism. 5 years later, this RAND report was published in a journal, and there he doesn't even consider the option of making it a unary postfix operator. He just said it's a binary operator. That's the way it is. However, 2 years later, Kobe, Elgott, and Wright said, no, it's actually mathematically cleaner to make it be a postfix star after all. And that is the form in which we use it today. In 1962, Brzozowski replaced the wedge operator with a plus sign symbol, and he introduced the postfix plus to indicate the case of one or more repetitions. In 1968, Ken Thompson published his paper on the regular expression search algorithm in CACM. And this is the earliest use I've managed to find of the vertical bar for an or, rather than a wedge. I'm not sure that's the very earliest use. I'm still trying to track down that little bit of history. 5 years after that, after Thompson had built his regular expression search algorithm into more than one text editor, Doug McElroy came along and said, I'm trying to search the Webster's Dictionary and it won't fit into the memory buffer of the editor. Could you please make it be a separate standalone tool? And thus grep was born. But it didn't implement all of regular expression notation, just enough to do what McElroy needed. So a couple years later, Al Aho comes along and creates egrep. He decides to do regular expressions whole hog. It appears that this is the point at which the question mark got thrown in to indicate the 0 or 1 case. I've not found any earlier case. I've asked Al Aho about this. He says, I don't remember inventing that. It's the obvious kind of thing to have thrown in at that time. He also put in full grouping symbols, and he used the vertical bar for or. Now the weird thing is that about this same time, the Alphard project started up at CMU in the mid-70s. The earliest published report I found on that is 1978. They were using regular expressions with Claney star, Claney plus, and a sharp sign symbol to indicate the 0 or 1 case. That lasted for between 3 and 5 years because by 1981, all CMU technical reports were using the question mark instead of the number sign. So it looked like there was a brief divergence in the notation, then it quickly converged. And I'm guessing that's because of the wide dispersion and use of egrep. Okay, so it took about 30 years for our notation for regular expressions to gel, and it's been fairly stable since then. But this development had almost nothing to do with the development of BNF. BNF kind of got started in 1958 with the Perlis and Samuelson report on the International Algebraic Language, which include forms for various language features. And if you look at the bottom of the first box, which describes function, they say function, they really mean function call in our terminology. The form of a function call f is an identifier followed by a number of parameters. And notice this very interesting ellipsis notation. It's got 3 symbols, but instead of being dots, they're these funny wiggles. I love that. Then in the bottom box, you can see various forms of arithmetic expressions. An arithmetic expression can be a number, or a variable, or a function call, or any of the expression forms down at the bottom, which includes addition and subtraction, multiplication, and so forth. And this is looking a little more like BNF, but isn't quite there. So the next year, John Backus is producing another report on the International Algebraic Language. And he reports that he was explicitly influenced by Emil Post's post-production notation. And so he wrote his production rules for a context-free grammar for the language in this form. And a single production may contain multiple alternatives. And you can see that you've got, on the left-hand side, you've got the non-terminal digit, and then you've got colon equivalence sign. And then to separate the alternatives, he writes the word or with an overline. You can see how a bunch of this notation had to be drawn in by hand. Okay, the next year, the report on ALGOL 60 is published in CACM. And Peter Nauer was the editor of that, and he changed the notation in part to make it a lot easier to keyboard. So the colon equivalence became colon equals sign. He replaced the or overline with the vertical bar. He kept the angle brackets, but he widened the angle brackets to 2 angle brackets around the non-terminals. And he made the decision that the names of the non-terminals would be identical to the English phrases that were being used in the informal text to describe the same thing, so as to make the notation more readable, to make it easier to connect the formal notation to the English text. So those are interesting design decisions. And this should look fairly familiar to you. But at the same time, in 1960, a completely different alternative was being developed, the COBOL metanotation. The COBOL report used a 2D notation. This is taken from the Codicil report. Choices were stacked vertically within braces, brackets indicated optional items, and the ellipsis indicated repetition of the preceding item. And an interesting thing about this report is that there's a section in the front of the report that says, here's the formal notation we're going to use to describe the syntax. And the use of brackets and braces are carefully documented, but the use of the ellipsis is taken for granted. 5 years later, 1965, PL1 comes out, and IBM's PL1 specification uses an interesting combination of BNF and COBOL metanotation. In the top box, you'll see a part of the expression syntax, and that is pure BNF, using braces for a grouping symbol. But in the middle box, you can see the description of a declaration, and they have used an ellipsis to indicate a non-zero number of repetitions of the preceding item, and if it's in brackets, it's optional. I find it really interesting that they wrote bracket, item, bracket, dot, 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 rather than putting item, dot, dot, dot in brackets. Item, dot, dot, dot in brackets, it looks a little less readable, but it has the virtue of making the parse unambiguous. If you put the item in brackets and then have dot, 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 you actually have multiple parses in the case where there are things missing, because you can always say, oh, something's missing here. And that gets repeated. Down at the bottom, you see a combination of the vertical stacking of the COBOL style with the brackets and the dot, dot, dots. Also in 1965, a lot of stuff cooking in the 60s. Niklaus Wirth brought out PL360, which is yet another programming language, the IBM 360. What's interesting here is he used a parameterized form of BNF. If you look in the middle of this box, there's a single BNF rule that says K register colon equals K register identifier, but his idea was that K could be replaced by any number of phrases, which in this case were data types, long, real, integer, real. So he made a single written rule stand for a number of actual rules. This reached full fruition in 1968 when Adrian van Wijngaarden introduced complete two-level grammar to describe ALGOL 68. The syntax of ALGOL 68 is described by a grammar that has an infinite number of productions, but those productions are generated by yet another grammar. And in effect, this allows him to do context-sensitive kinds of things, such as type checking, right in the grammar. So it's a pretty amazing formalism, almost completely unreadable. There's still a few fans of it today, but it's not used much anymore. 1970, the BLISS language is described using BNF, but for some reason they used a right arrow instead of colon equals. You can see that in the example here. And this notation is taken, for granted in the report. They don't even bother to describe the BNF notation. On the other hand, 10 years later, the Digital Equipment Corporation BLISS documentation used PL1 style syntax descriptions rather than this pure BNF. Okay, so a lot of things happened in the 60s, a few things happened in the 70s, and one thing that happened in the 70s, I can remember this, is that we thought that syntax charts were going to take over from BNF. This new two-dimensional graphical formalism was introduced. In 72, a Burroughs language used syntax charts only to describe their syntax. The famous Gentzen and Wirth book on the PASCAL user manual and report used both BNF, ALGOL 60 style, and syntax charts, and here's an example. This is the syntax of an unsigned number literal. The Fortran 78 standard, which was published in SIGPLAN notices, used syntax charts plus PL1 style BNF. And in 1979, the RED language used syntax charts only. So syntax charts were considered respectable enough to be used in a competitor to become Ada. Unfortunately, red lost and green became Ada, and nothing wrong with green. But the point is, syntax charts were respectable by the end of the 70s, and then kind of died out in the early 80s. So in 1977, things come to a head, and Niklaus Wirth publishes, "What can we do about the unnecessary diversity of notation for syntactic definitions?" He observes that there are dozens of variations of BNF out there, and their proliferation is becoming confusing, and the solution is to propose yet another one. And in this box is the description in the paper. Here he gives a definition of his particular variation of BNF in its own syntax. So this is the Wirth BNF for the Wirth BNF. And this is the first example I found of metacircular BNF. Repetition is indicated by curly brackets. Okay, so instead of curly brackets being used for grouping, they're now being used for repetition. Square brackets still mean optionality, and the parentheses are used for pure grouping. And the vertical bar is used. And no longer do you need angle brackets around the non-terminals, because instead the terminals are delimited by quote marks. And finally, he decided to be pretty to have a definite end to each rule, so every rule is ended with a period. And this notation kind of catches on, and it goes through several variations, and about 20 years later it becomes an ISO standard, extended BNF, which is fairly similar to Wirth's notation. Okay, a quick rundown of some other BNF variants. In 1976, Stanford's SAIL language uses BNF, but instead of using a vertical bar to separate alternatives, it just repeats the colon equals. Why? I have no idea. In 78, the Alphard project used regular expressions, a funny version of regular expressions, that, as I said before, but it uses them in their BNF notation. And this is the first example I found of actually integrating regular expression notation for indicating the repetition with BNF. In 1980, the Ada specification, formerly green, used BNF, but instead of colon equals, it uses a boldface word is, and the boldface word or for the vertical bar. That boldface word or kind of reminds me of Backus's notation. In 1981, the CMU front-end generator and interface description language used regular expressions in BNF, but now they converted to the use of the question mark for the optional case. I was at CMU in the early 80s, and I think that their notation influenced me and Harbison when we published our books on C and commonless in 1984. We also used regular expressions in BNF. In 1995, a decade later, the Python reference manual uses the Claney star and plus in BNF, but they don't use question mark for the optional items, they use brackets. PASCAL 98 report uses BNF, but instead of colon equals, it uses a little arrow. Maybe they were influenced by BLISS, I don't know. And it also uses an ellipsis in the productions. In 1998, same time as the Haskell report, the Ruby language reference manual uses Claney star and plus in what they call pseudo BNF, that's their term, which is a little bit like Wirth's notation, but they use brackets for optional items. And the last set of variations I want to show you is C-style BNF, which has been very popular for 35 years. In 1978, Karen and Ritchie published a C programming language, and their format for grammar rules reduces the colon equals to a simple colon. Instead of separating alternatives with a written term, like vertical bar, they just stack them vertically, and they don't even bother to put them in braces. You're supposed to recognize that vertical stacking. Tufti would be proud. They're making white space do the work of symbols. This is great. And then this extra rule, which is that if the alternatives are all single symbols, you can string them out horizontally instead of vertically by using this special phrase one of after the colon. Widely used notation is used in 1985 for the C++, in 96 for Java, in 2000 for C#, and in 2012 for F#, although the F# specification also uses a special treatment of ellipsis. curiously defined as a postfix operator rather than as a separator, although they use it as a separator, they define it as postfix. There may be a problem there, not sure. I need to study more closely. Okay, we have seen a wild variety of BNF variations in the last 6 decades. And my assessment is that, Wirth to the contrary, this hasn't been a problem. It's like having a whole pile of dialects of Latin. You've got Spanish and French and Portuguese and Italian, and they all sort of look alike. Maybe it's even as broad as the Indo-European language. But if you're familiar with the idea of BNF, because all of these notations present roughly the same pieces in the same order, you can usually figure out the syntax and figure out what the author is about. It'd be nice if we had a single notation, but a little bit of variety doesn't seem to have hurt. That's okay. Okay, but now I'd like to show you my last example of BNF, and this is the slide I showed you earlier and said we'd return to. This is BNF as used in computer science metanotation. It's recognizably BNF, and yet it is very different from all the other examples we've seen in a number of ways. One is that the non-terminals are all single letters, many of them Greek letters. Another is that, as in this declaration of types, we're in the custom sometimes of putting more than one non-terminal on the left of a rule to mean we can use any of those non-terminals and that production applies to it. We've lost what Knuth had praised about Nauer's notation, which is that the non-terminals were a readable English phrase and therefore self-documenting. The single letters are no longer self-documenting, so some authors use this very structured style of comments, where the comments that I've shown in blue, either ahead of the rules in the case of expressions and types, or off to the left, are a comment on what the non-terminal means on the left. And if the cases are strung out separately, there may be comments indicating what the individual alternatives mean on the right. So these comments. And we see in the bottom line and the third line from the bottom, the use of overline as a repetition notation, a very concise notation, which we will be looking at later. My point is, this is yet again a very different form of BNF. And why is it so different? Why is it so different from all the variations we see in the programming language specifications? I conjecture there is a very strong evolutionary pressure that has driven computer science metanotation to trade off readability for concision, and that is conference page limits. I'm not kidding. That is an important evolutionary pressure. And as we develop more and more complicated type-checking algorithms and other descriptions of programming languages and still have the same page limits, we're being driven to compress the notation more and more. As we will see, the overlying notation didn't appear right away. And I think that was a desperation move to try to save horizontal space. Okay, so that's something to keep in the back of your mind. Okay, now, 2 other conventions have come into play in the use of BNF, and I'm going to discuss these fairly explicitly. If we took the definition of BNF literally, which means that wherever you see a non-terminal, you can replace it with a string derived from that non-terminal, then if we add a sentence such as, a value of type ta may be assigned to any variable of type ta. Great. We see the first ta and we expand it to int, we see the second ta, we expand it to bool, and we see a value of type int may be assigned to any variable of type bool. Cool. Not what we want. Instead, we have this convention about consistent substitution. Within a given context, and exactly what context means is kind of vague. It might be a sentence or it might be an inference rule. But within some context, if the same non-terminal is mentioned more than once, the same expansion must be used for each occurrence. This allows us to talk about things. We need to be able to refer to things more than once as we talk about them. So a consistent substitution, we say, okay, here's this sentence, that's a context. Ta appears more than once. We will choose to expand ta to int in every place it appears. Now we say a value of type int may be assigned to any variable of type int. This makes sense. Here's a second convention. The decorated, I call this decorated non-terminals convention. What I mean by decoration is things like subscripts and primes and hats and other accent marks. If we took the definition of BNF literally, that every non-terminal can be replaced by a string derived from that non-terminal, then a sentence such as, if ta1 equals ta2, then ta1 is a subtype of ta2. Then if we chose ta to be expanded to int, then this would expand to, if int sub 1 equals int sub 2, then int sub 1 is a subtype of int sub 2. Well, that might make sense in some programming language, but usually it's not the kind of thing we're trying to write. Instead, we have this convention that says that if you decorate a non-terminal, then each distinct decoration becomes a distinct non-terminal, but it has the same productions as the undecorated form. So I can choose to expand ta1 consistently to int and ta2 to bool. And I get this true sentence: if int equals bool, then int is a subtype of bool. In fact, int is not equal to bool, it's a false antecedent, so the conditional is true. I could also expand both ta1 and ta2 to int, and I get if int equals int, then int is a subtype of int. That's also true. Okay, decorated nonterminals convention. Okay, so that's what I want to say about BNF, but BNF will wander back into our story later on. Okay, take a deep breath. We're almost halfway done. I want to talk about substitution. Another thing happening in the 20th century as they're trying to work out logic. In 1932, Alonzo Church uses this notation for substitution: the letter S, a variable up top, a term to substitute for it below, and then a subject expression U. So this is the substitution in U of y for x. Notice that the variable we substituted for is on top. I still haven't figured out how it eventually got down to the bottom. And that's more history that needs to be researched. But in Church's notation, the variable's on top, the replacing term is on the bottom. And this appears again in 1941 when he publishes his monumental work, The Calculi of Lambda Conversion. To replace any part, lambda xm applied to n of a formula by substitute n for x and m, provided the bound variables are distinct both from x and from the v variables n. So a very important transformation rule in his calculus. Okay. We've seen a wide variety of substitution notation as well. I did this survey of 43 years of POPL, and I discovered that there were 28 varieties of substitution notation being used. I was not expecting that. I was expecting 5 or 6. 28 different variations on substitution notation. I've highlighted the 5 most popular during this period. Their usage has grown over time. Metanotation is used in over half of POPL papers in the last 20 years. In the last 5 years, substitution has been used in over 1/3 of them. I went back and counted that more carefully. By far, the most popular version is E bracket V over X bracket, where I'm pronouncing the slash as over. I actually should say slash. Second most popular is the same thing, but in prefix form instead of postfix form. The third most popular is this version that uses braces instead of brackets. Fourth most popular actually doesn't come into use in POPL till 1988. And I strongly suspect it was influenced by its use by H.P. Barendrecht in his great book, The Lambda Calculus. It's Syntax and Semantics. That was published in 1980, and then 8 years later, we see his notation filtering into POPL. And then the fifth most popular is this one that uses the maps to arrow. Okay, so that's my analysis of POPL. Then later I went back and looked at the last 3 years of OOPSLA and ICFP and PLDI and PPoPP. And I discovered that 3 more notations had appeared. So we don't have Howard Johnson's, we've got Baskin-Robbins, we've got 31 varieties of ice cream here. Those are old-timey references to old ice cream chains. And those are yet variations of what we've seen before. So now we can say that during the last 43 years, 31 different notations have been used for substitution. Of these 31, 15 have been used at POPL within the last 5 years. And the 5 additional ones highlighted in the pinky color were used at other SIGPLAN conferences in the last 3 years. So we can say in the last 5 years, 20 out of 31 notations historically seen have been used. And a chart I don't have in these slides, but if you graph the number of substitution notations per 5-year interval, that has been steadily growing over time. So it's not that we're changing out one fad for another. It's that we are continuing to add to our collection and not subtracting it from it very much. So, is this a problem? The variety of BNF hasn't been a problem. Well, I am detecting some problems with this variety of substitution notation. There are several such problems. Here's a small problem. It's sort of weird to have in live use the use of both a left arrow and a right arrow, but always to have X on the left. I expected X always to be at the tail of the arrow or something. But authors who reverse the arrow don't reverse the variables, so that's a possible small confusion. And the same is true when authors use braces rather than brackets. But it turns out this is only a small problem because this particular variation of notation is actually fairly rare. It's appeared in half a dozen papers. Here's a moderate problem. By far the most popular problem is postfix with brackets and a slash. E with V substituted for X. But about once every 5 years, we're seeing an author get it backwards and put the X before the V, but otherwise the identical notation. And you can't count on the variable names to tip you off because different authors use different variable names. The actual papers don't use X and V. They could use any 2 letters. So you see the slash and you're really not sure which is the one being substituted for. One paper published in the last year actually used both forms in the same paper, and without making any remark about their substitution notation, they took it for granted. Now, maybe one of the uses was a typo, but it got past all the referees and it got published in a conference. Referees, are you looking at the notation very carefully? Please check the notation very carefully. But here's the huge problem. These forms using the maps to arrow and colon equals, and variants that are maybe prefixed rather than postfixed, and variants that may use braces rather than brackets, are very frequently used for substitution. They've appeared in about 1/6 of all POPL papers that use substitution. But these notations are also widely used for a completely distinct purpose, namely function update, also known as map update or storage update. And this is the operation defined by this formula down here. F updated so that x maps to v when applied to z means that if z is x, you're going to return v. And otherwise, you're going to return f of z. So this is an update to a function. And I can understand the metaphor, the analogy that leads people to think that this is also a reasonable notation for substitution. Well, we're going through E and we're mapping all the x's to v's, but substitution is a much more complicated operation. It's not just mapping things, it's also doing a tree traversal, and it's also enforcing the capture-free substitution rule. And that is a very complicated mechanism that is not to be confused with a simple function. Using both of these notations in one paper can make it very hard to read. And as a referee, I've encountered a lot of that in the last 20 years, I want to tell you. And finally, it's a problem because lately, meaning in the last 5 to 10 years, authors are taking these notations for granted. They're not spelling out their papers exactly what they're using those notations for. They're assuming it. And they are ambiguous because they've been used in these two different ways. An unpublished paper I read just last month, and I've anonymized it slightly to protect the guilty, read roughly like this. At the end of a paragraph, they very commendably say, substitution of a term t for variable y and e is denoted by this notation. E with braces, y maps to t. Now consider this function. F with p0 maps to q0 and p1 maps to q1. And I glitch and say, huh? Wait, is this an example of that substitution notation they just called out? But the expression is missing. Maybe it really is a function. They didn't tell me about using this for a function notation. They only talked about using maps to in the substitution notation. Finally tracked it down. The substitution notation was used in the paper, but not for another 6 pages. For some reason, they told me about it right before they were about to use the maps to arrow for some completely different purpose. And this cost me like 10 minutes trying to referee the paper. So, authors, don't do this. So, I have some recommendations here. You don't have to take them, but my recommendations are that, first of all, postfix forms are clearly more popular than prefix forms by about 2 to 1. So if you want to maximize the chances that your notation will be recognized, use postfix form. I recommend that you use either the slash, which is by far the most popular, or an arrow, but not a maps to arrow, to the right, which is arguably clearer. Never use a left arrow. If you use slash, do not make the name smaller or superscript or subscript them. That seems to be a fashion, particularly in Europe. But making the names smaller only makes them less readable. We've already got problems with the fonts in papers being too small. So don't make the font smaller. Reserve the maps to arrow for function update. Reserve colon equals for storage update. That's a convention I'm going to adopt in all my papers in the future. I recommend it to you. And I suggest making a distinction between brackets and braces. I suggest using brackets for operators and braces for collections. So in the first column of this chart, I show applications. And I use square brackets for substitution, square brackets for map update, square brackets for heap update. And if I'm not actually applying it, we just want a bare operator that I can give it, and I can give it name it by using a symbol. Then I can say a substitution sigma equals v/x in brackets, or a map update u x maps to v in brackets. But if I've got a collection, if I'm describing a data structure, I intend to use braces from now on. We'll see whether it catches on. By the way, one reason I think that people don't like the slash is because they think it isn't mnemonic. And in fact, people get it backwards and they forget which one is on top and which is on the bottom. I offer this mnemonic that for E with v/x, read that as within E, v supersedes x. Remember the original Latin meaning of the word supersede is to sit over or sit on top of. So the thing that sits on top supersedes the thing beneath it. If you're going to use the arrow, then you can say within E, X becomes V. Okay, that's what I have to say about substitution. Let's talk about overline. This has a fascinating history. Much of this data is taken from Florian Cajori's monumental work on mathematical notation. In 1484, Chuquet uses an underline to group symbols together. In 1525, Christoph Rudolph uses the tick mark sign kind of thing to indicate taking a square root, and he also uses a dot to indicate the grouping, and you can see the example up there. In 1556, Tartaglia uses parentheses for mathematical grouping, and a century later, almost, Ottred uses double dots to indicate grouping. Why did he use 2 dots instead of 1? He wanted to use a single dot for something else, that's why. 1631, at the same time, Harriot uses a long overbrace with that surge sign for grouping. And in 1637, Descartes attached a vinculum, that's the old-fashioned word for an overline, attached a vinculum to the little checkmark symbol, producing the modern square root symbol, and that has been stable ever since. And that's why the square root symbol has that long line over the top. That's a descendant of a use of overline for grouping things together. 3 years later, Jan Stampoen took no chances and used all 3 together. He used parentheses and an overline and a dot, just to make sure. 1646, van Schoten used overline for grouping while editing Vieta's works. In 1702, Leibniz began using parentheses in preference to overline because he said this will make much less work for the typesetters, and he was worried about the efficiency of the typesetting equipment. So he said, let's switch from overline to parentheses. And 6 years later, Acta Eruditorum, I love the name of that journal, the Acts of the Erudite. Acta Eruditorum officially adopts Leibnizian symbolism and says, let's use parentheses in all our papers from now on. The next year, Maupertuis uses square brackets in addition to or instead of parentheses. In 1728, Euler and the 2 younger Bernoullis started using parentheses and brackets exclusively in their publications, and Cajori comments, the constant use of parentheses in the stream of articles from the pen of Euler, he was very prolific, that appeared during the 18th century contributed vastly towards accustoming mathematicians to their use. So we can thank Euler that we've got parentheses now. And yet, 130 years later, Giuseppe Peano, the one of Peano arithmetic, reintroduces dots. They'd fallen into disuse for a century and a half. He decides to bring them back. So here's an example. When you write A:(BC dot D, that means that parenthesized expression. The idea is there are no dots between the B and C, so they bind most tightly. Then the place where there's 1 dot binds next most tightly, and 2 dots is the weakest of all. So the number of dots indicates binding weakness, which is a play on our usual term for binding strength, which is the inverse. In 1881, Gibbs uses an overline as a part of vector notation. That may seem like a non sequitur, but that'll come up on the next slide. And in 1910, Russell and Whitehead, in their monumental Principia Mathematica, their attempts to axiomatize all of mathematics and make everything provable, use Peano's dot notation, which is unfortunate for us a century later because it makes his work much less accessible because we're used to parentheses. The dots are a little hard to read, but brilliant work. Unfortunately, then a couple of decades later, we got the proofs of undecidability and said, sorry guys, you lose, you really can't prove everything after all. Too bad. Anyway, so in 2 slides, I summarized 3 notations, dots, parentheses, and overlines, duking it out in competition for 5 centuries, as to which will become the popular notation for grouping. And as you'll see, that has now gone on for almost 6 centuries. Now let's talk a little about vectors, which I alluded to in the previous slide. Okay, you remember Descartes introduced Cartesian coordinates, and you could graph points algebraically in the xy plane, leading to the development of algebraic geometry. In 1813, Argand adapted this to the graphing of complex numbers and producing the Argand diagram, and speaks of the square root of -1 as describing a rotation in the plane. In fact, other complex numbers can describe other rotations in the plane. And he proposes the notation AB with an arrow over it to indicate a vector from point A to point B. 20 years later, Hamilton recast the theory of complex numbers as a purely algebraic structure on pairs of reals. He doesn't want to think about the square root of -1 at all. He just wants to think about these pairs of real numbers and an algebra on them. He's interested in the algebraic structure, the algebraic laws, commutativity, associativity, distributivity, all that. So he recasts complex numbers as pairs, and then spends the next 10 years trying to generalize it to triplets and quadruplets and higher tuples. And he's very frustrated for about 10 years, and then suddenly he stumbles upon the quaternions, and famously carves an equation on the Broom Bridge, which is no longer there, but there's a plaque there now. And the quaternions, it turns out, are this very special generalization of complex numbers. They turn out, although they have 4 components, they turn out to be good for describing rotations in 3 space. But unfortunately, it turns out to be something of an odd duck. It does not further generalize. We've got something special for 2 dimensions, something special for 3 dimensions, and there isn't anything else of this kind. Between 44 and 46, Hamilton reformulated the quaternions without using IJK coordinates. He was trying to avoid depending on a particular coordinate system, and instead formulated essentially using vector algebra. So he separates a quaternion into the scalar part, that's A, and a 3-dimensional vector that is imaginary. And James Clerk Maxwell used quaternions in his works describing electricity and magnetism. He also interjected some mild criticism saying, gee, these things are hard to work with. In 1881, Gibbs establishes dot and cross as the standard symbols for dot and cross product. And the next year, Oliver Heaviside advocates ditching the scalars and quaternions and just using the vectors. And he reformulates Maxwell's electricity and magnetism theories using a pure vector notation. And the motivation is that using just the vector part makes more physical sense. Because if you view a quaternion as the sum of a scalar and an imaginary vector, if you try to find the length of the vector by squaring it, that is taking a dot product with itself, the problem is the result of that dot product is negative because the vector was imaginary. So you have to compensate for that before taking the square root. And in general, when you formulate physics using quaternions, the signs keep coming out in non-intuitive ways, and that really bugged people. And so in the early 1890s, for about 5 years, there's this big fight between the quaternionists and the vectorists. And the quaternionists said, the quaternions have a more consistent algebra, it's a more beautiful theory. And the vectorists said, yeah, the vectors are ugly, yeah, we agree the cross product not only is not commutative, it's not even associative, but it gets the job done and makes sense to physicists. And the vectorists won. And hooray for them, because vectors generalize to any number of dimensions, and this is great. So this brings us back to POPL. In the 1970s, both A with an arrow over it and A with an overline over it are used to denote a vector, list, or sequence. Usually the word as vector is used in earliest papers. They say, let A with an arrow over it be a vector of A's, that is, A sub 1 dot 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 A sub n. There was one early paper in 78 that used an overline over x colon t to describe a sequence of variable declarations. That was actually an historical outlier, so I'm going to ignore that for now. It was not until 81 that overline notation was even taken for granted at POPL by a paper. But it always denoted an enclosed sequence. It denoted a sequence of things enclosed in angle brackets or parentheses or something like that. It's not until 1989, for the first time at POPL, that the notation of an arrow indicates an unenclosed sequence of things. So up to this point, you can say that the semantic model of this overline or over arrow notation is that it marks a variable as representing a vector or sequence, and there's a syntactic model that you can substitute for it by making copies of the overline variable names and attaching subscripts, starting from 1. And these copies are probably enclosed and maybe comma-separated. But that's how things were for about 15 years, 16 years. In 1990, we see the first explicit claim that I could find that the elements may be metasyntactic variables. In 1990, we also see the first use of an implicit unit of replication. Check this out. We say that if M is a sequence and if sigma is a sequence, we write M overline, cola, sigma overline, not to mean a bunch of M's, a colon, and a bunch of sigmas, but to mean M1 colon sigma 1 dot 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 MK colon sigma K. So the stuff that's being replicated is bigger than the stuff that's being overlined. That's an innovation. In 1993, we see the first explicit claim that an overline may apply to any syntactic object, not just a variable name. And in 1994, we see the first use of overline on a syntactic fragment that contains an operator, in this case a semicolon for combining coercions, that contains an operator rather than just a separation symbol like a colon in a variable declaration. So we're in the mid-90s already. And we're beginning to see problems. Okay, We have already seen m overline colon sigma overline being used to mean that the variable declaration is being replicated. And later we see things like t overline, a space, and x overline for a similar replication of Java style or C style variable declarations. So this raises a question. When we see this convention, just how big is this implicit unit of syntactic replication? You know, what is its scope? Now others have written m colon sigma with an overline over the whole thing to mean that same thing. Now the unit of syntactic replication is clear. What you're replicating is m colon sigma. But now this raises a different question. Where should the subscripts be attached? Why should the result be m1 colon sigma 1 rather than, say, replicating the whole thing, m colon sigma, and attaching just one subscript, which had been sort of the prior syntactic model? Or why shouldn't we attach a subscript to the colon as well as to the letters? Now, we can invent reasons for this, but no one had written them down yet. These are being taken for granted. Okay, continued development. In '94, we see the first use of nested overlines. If you can put an overline over any syntactic category, sure, you can put one over an overline. In '96, we see the first explicit definition of the over arrow notation as meaning an unenclosed comma-separated list. In '96, we see overline notation taken for granted in a paper, but a first explicit statement of the equal length convention. We implicitly assume that when we say z overline slash y overline, this is in the context of substitution notation, that the sequence y is linear and of the same length as z. So that's a really important convention that nobody had enunciated before, but had been taken for granted. That when you use overline notation and more than one vector is involved, they need to be the same length. Also in '96, the first use of tilde for repetition. Up to now, we've seen overlines and over arrows. Now we're seeing a tilde used for this purpose. Why? Because this is a paper about pi calculus. And pi calculus is also already using overline for another purpose, to distinguish input ports from output ports. So when they suddenly saw the need to adapt this overline notation, they had to choose a different symbol. '97, we see another pi calculus paper using tilde. This has the first statement I could find of the rule of general pointwise extension. By abuse of notation, operations on singletons are explicitly extended pointwise to sequences. This is an attempt, I think, to address that question of how big is the overline? What is the unit of replication? But we immediately run into a problem with this, and in fact, in the same paper. So from that paper, we have this expression. What is the meaning of gamma, b tilde, equals substitute a bunch of t's for a bunch of x's and a bunch of p's? Well, if we regard substitution as a pointwise operator of three singleton arguments, and equality as a pointwise operator on two arguments, then we can fully extend this equation pointwise. So we replicate the entire equation. We can see that this expression stands for gamma b1 equals substitute t1 for x1 and p1, and so forth up to the n. Gamma of b sub n equals substitute t sub n for x sub n and p sub n. And that is a consistent interpretation of their comment about pointwise generalization to that equation. Unfortunately, that's not what the authors intended. A careful semantic analysis of the rest of the paper indicates that the authors really wanted that equation to stand for a different conjunction of assertions shown at the bottom of the slide. And their idea was in the substitution, t and x have to be the same length, and completely independently, b and p have to be the same length. And they wanted to apply the same substitution to all the p's in order to get the gamma b's. There's a reasonable thing to try to write. This notation wasn't up to it. So, a possible solution is nested overlines. Instead of writing, and here I've switched to overline notation, instead of writing overline p equals overline x for, overline v for overline x and overline q, some authors write with a big overline over the whole thing, p equals, and then another overline over v slash x to indicate that they're separate, applies to q. And I find it fascinating that the overline notation got into computer science notation initially as an outgrowth of vector notation, but by this point it has reacquired its ancient ability to indicate grouping. And so the use of it as vector notation, the use of it as grouping have converged, and today it serves both purposes simultaneously. I think this is a really interesting innovation. So superficially, this approach seems natural, but how do we know that it really means what that equation meant on the previous page? As shown in this first set of equations where both v and x are one-dimensional. And how do we know it really doesn't mean there are a bunch of v's and a bunch of x's and that v and x are really two-dimensional? How do we know? Now, even without nesting, some authors write things like this. Here's a premise with an overline over it, and in the context of gamma, X has type T. And the intention is that in the context of gamma, X sub 1 has type T sub 1, and X sub 2 has type C sub 2, and both so forth. But how do we know that there aren't a bunch of gammas? How do we know that gamma isn't also supposed to get a subscript? And we would have the same problem with putting an overline over this more complicated thing. Why do B and T and X and P get subscripts, but gamma doesn't? Now, it's possible to do a global dimensional analysis, but it's difficult, and I've actually had to do this in interpreting a bunch of POPL papers. You say, oh, well, the gamma is under the overline, but here's this other place in this other part of the rule where gamma is not over and underlined. So gamma must be intended to be scalar, and therefore it's implicitly replicated in this rule. And you can do that kind of thing. You can sort of tell which variables are supposed to be one-dimensional and which are supposed to be two-dimensional. But it requires a lot of interpretation on the reader's part, and furthermore, just semantic analysis. And I much prefer to have purely syntactic explanations where possible. But where we finally come up with the essential contradiction is this. Actual live uses in literature. In about the last 15 years, we found we want both of these things. When doing type analysis algorithms, in particular when looking at parametric types, we're dealing with expressing the bounds on types. We need to do substitutions into the bounds to get new bounds. So we typically want a big overline, P equals little overline V slash X applied to Q. We want that to mean each P is derived from some Q, but the same substitution is used each time. On the other hand, when we're describing case syntax in a functional language, we want to write things like case E of, here's a bunch of case clauses, and within each case clause there are a bunch of variables, and the variables can be different in each case clause. In fact, you can have a different number of variables in each case clause. So this is the essential contradiction, the same notation, we're trying to use it for two different things. We can't have it both ways. What's the way out? Let's talk a little about what we want from overline notation. Let's try to analyze it from a language analysis point of view. We know an overline string to expand to any number of copies of string. This is more concise than the ellipsis notation. There are questions about how the copies are separated, whether a comma is there. I'm not going to worry about that for now. And we have a convention that each copy of string may be expanded differently. If we say a function call looks like f, and then in parentheses, E overline, we want each expression to be able to expand into each E can become a different expression in order to become the argument expression. So we have this convention that when you make copies through overline, the copies may be expanded differently. But if overline string itself is mentioned more than once in a given context, such as a sentence, we want each of those expansions to be the same. So that's another constraint. And in fact, when we use overline to make copies of string, within each copy of the string, if there are multiple occurrences of the same BNF non-terminal, we want them to be expanded in the same way. The general rule is if two copies actually are represented by two different sets of ink on the page, we want to require them to be expanded the same. But if the copies came from the same set of ink on the page and the copies are just made by overline, we want to be able to expand them differently. It's a very strange set of conventions. If the variable v occurs within string, copy I of the string needs to refer to v sub I. This is the vector notation part of the convention. And all variables occurring in the string must have the same length so the substring notation will work. So a formal theory of overline expansion has to track two different kinds of constraints. The requirements for identical expansion and the requirements that variables have the same length. And various constraints suggest that a formal expansion process should expand overlines first, then BNF, then substitutions. So to solve the essential contradiction, I propose to add one more thing to the notation. I want to propose to borrow an idea from quasiquoting. Quasiquoting, here's an example from Common Lisp. Backquote and then an S expression means make a copy of the S expression. But where you see a comma, that means except here. It means don't make a copy. Instead, use the value of that expression and stick it in there. That's the quasiquoting idea. We also see this in printf strings. Printf means print this string. But wherever you see a percent sign, do something different. So there's an except here escape. We also use this idea for parallelism in connection machine Lisp about 30 years ago. Alpha followed by an expression means evaluate many copies of this expression in parallel. But the bullet means except here. The value of the expression following the bullet is a vector, so please use a different vector element in each copy. And this is the way in which connection machine lists happen to express the idea of mapping. Okay. I've said that in the overline notation that if you explicitly write different copies, they have to be expanded the same. But if copies are made by overline, they can be different. We can also override the first rule by using decoration. So if we mention E twice in the same sentence, it has to be expanded the same way. Would we say E1 and E2, then E1 may be expanded differently from E2. So we have a way to explicitly override that default. What we need is a way to override the other thing that says that copies made by an overline can be expanded differently. So I propose this modification. I want to add underlines. And I propose this modification to this rule for overline notation. Each copy of the string may be expanded differently, but underline means except here. Any underlined portion of the string must be expanded the same way in each copy. And therefore, for examples, we can write, the case expression is written as before, and you just have an overline of the case clause, an overline of the variables, and that means, yeah, actually, you can have different variables in each case clause. But because I want the same in the first line, I want the same substitution in each outer copy, I underline the substitution symbol. And that says, make sure this gets expanded the same way in each copy. And in the other two examples, we do the same thing. In the computation of gamma b, I can say I want the same substitution for each p, and I can also say I want gamma to be the same in each copy of this overall string. And in the simpler example down below, it's simply gamma, in the context of gamma, x has type t. Because I underline gamma, I'm using the same gamma each time, but it's a different x and a different t in each copy. And we have this very nice syntactic rule. The dimensionality of each variable is simply the number of overlines minus the number of underlines. Gamma has one overline and one underline, it's a scalar. X has one overline, it's a vector, and so forth. So that is my proposal. And I have a formal model for overline expansion. For lack of time, I'm not going to get too deeply into it. But roughly speaking, the solution is to integrate the old subscript attachment model. And then the usual rules for B&L non-terminals, the decoration rule, will enforce the necessary same expansion or non-same expansion constraints. And you have to track the length constraint separately. So roughly speaking, to expand an outermost overline, you choose a length for a number of copies you made. You replace the overline string with n copies of the string. In copy k, you have to decide whether to attach a subscript. So I propose the rule that you always attach subscripts to BNF non-terminals and to single letters. And if you want it anywhere else, there's a more elaborate version of the notation that does that. And you have to keep track of the same lengths. In each copy, from any underline material, remove just one underline in the copy, and now expand the replacement material. The net effect is you expand the overlines from the outside in, and the subscript attachment rule makes sure that everything works, and it enforces the correct same expansion constraints. I'm going to skip ahead. What about cases that simple overlines can't handle? Some authors have tried using letters as subscripts to indicate the attachment points. The problem is that the binding point of the variable is not indicated explicitly. Other writers, look at the bottom of this slide, put the binding point next to the overline at the right. So in the first example here, the upper overline binds index I, the lower overline binds index J, and the subscript points can be attached, attachment points can be indicated explicitly. And in a more elaborate version of this, you can express the appropriate ranges for those bindings as well. I think these are pretty good notations. Okay, I've got about 3 more minutes left. I'd like to discuss ellipsis. Dot notation has been widely used for hundreds of years. It has a 500-year history. I'll spare you that history. Most readers have encountered this notation already. It is a notation that is rarely introduced properly. Mostly it is just used without explanation, as Roland Backhouse writing in his book. In the past, we've used ellipsis to explain overline. In all the POPL papers where overline is explained at all, they typically say x over bar means x1 dot 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 x sub n. Maybe there are commas there. But now that raises the question, doesn't beg the question, but it raises it. What does the dot 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 mean? My proposal going forward is that if we can provide a formal description of the overline notation without using dot dot dot, which I've already alluded to, I'm not showing the full formal development, but you can provide a formal definition of overline without using dot 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 anywhere. And this means that you can then explain the ellipsis notation by a formal transformation to the overline notation. And I've begun a development of that as well. Ellipsis notation has many forms. It's very difficult. And to make it even more complicated, if you look at this first example here, sometimes when you write dot, 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 it just means don't care. I literally don't care what comes in here. But many other times when you write dot, 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 it means I care deeply what comes here. It has to conform to a pattern indicated by the two examples at either end. And so distinguishing those two cases is tricky. The basic idea is to provide a standard set of usage patterns to be supported. For each use of ellipsis, the expansion must identify massing usage pattern. Each pattern has to include one or more ellipses, some number of copies as a separator string, and some matchable strings. And the idea is to use unification type matching on the matchable strings to find a common structure, and thereby construct an overline notation. So let me just run you through a simple example. This first example. The example is x sub 0, comma, dot, 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 comma, x sub n minus 1. The separator is comma. There's an ellipsis in there. The matchable strings are x sub 1 and x sub n. You do some unification, discover that the common structure is x sub I, where with the substitution 0 for I and n minus 1 for I. And then having discovered those substitutions, it's very easy to construct the overline notation, overline of x sub I, where I ranges from 0 to n minus 1. And example 2 shows a different form, a sub 1, so a1, b1, o plus, a2, b2, o plus, dot, dot, dot. The separator is o plus. The matchable strings are a1, b1, and a2, b2. You find the common structure ai, bi with the relevant substitutions. This particular pattern requires verification that 1 and 2 are consecutive integers. And then you can construct an appropriate overline notation. So here is an example of the formal description of that process for example 1, and it's full of formal notation. I'm not going to walk you through it here, but I've tried to work this out. I think it's time to wrap it up. My conclusions are that computer science metanotation is a programming language with its own distinctive syntax, semantics, and idioms. It can be executed in a style similar to Prolog. It probably has other idioms we haven't explored. CSM should be an explicit object of study in our community. It's a living language, and it's changed over the years. Recent changes in the last 15 years have caused problems. I've shown you some of these, and I've proposed some fixes. I believe that we should develop a complete formal theory of this language, including the overline notation and the ellipsis notation and iterators, including the nested cases, and their interaction with BNF and substitution. They're fairly complicated. I've made a start toward this. I'd love to get other people involved. I believe that we should apply the techniques that we develop for so many other programming languages to computer science metanotation. We should build interpreters, compilers, IDEs, correctness checkers, proof checkers, and other tools. And why am I giving this talk to PPoPP instead of one of the other conferences? I believe there are interesting opportunities for parallel execution of CSM. The repetition notations cry out for a parallel implementation. And I would love to see this, a parallel implementation of this language done right, rather than seeing a sequential version done first and then we have to undo it. And I think there are plenty of interesting opportunities for use of parallel algorithms and the associated tools. This is the audience I wanted to talk to about this first. So please think about parallel implementations of this notation. I think there are wonderful opportunities. And what I'm looking forward to is that I think that the mechanization of this language and the development of tools is going to change the language in yet further interesting ways. And that's what I really relish. Thank you. I'm sorry, I cannot hear you.
Okay, try again.
Better.
So it feels like React, since you made your way work in this area, which is just Metanotation and subset CSM. And I'm just wondering if you can comment on how you see it, option, some tools,
Yes, that system and also the K framework. You can go to kframework.org. We are beginning to see things that are like that. And they're like it in the same way that C is like Java. But I would like something that addresses my particular dialect. CSM is what we're using in the papers. I would like to mechanize specifically that. And we've taken steps toward that, which is great. I want to take the next steps. I want an IDE that lets me write that two-dimensional notation, the same stuff that appears in the papers. Anything else involves a mental translation.
So, I was thinking about Python programming and hearing your talk, and there have been attempts to make real code more readable, like in the Fortress project, where you had math
Yeah, your point is very well taken, that I've completely ignored pseudocode, which is another very widely used notation and also somewhat abused. And in fact, pseudocode and CSM can be used together. I had to limit the scope of this talk. I didn't want to try to tackle everything at once, but I agree that pseudocode should be tackled in exactly the same way and for exactly the same reasons, and that there are opportunities for parallelism there as well. Yes, the question is, what can we do about the evolutionary pressure of conference page limits, because there are problems with making conference papers too long. I never said that this pressure was a bad thing, and I never said that page limits were a bad thing. They're there for other reasons. I'm simply observing that that pressure is causing a language to come out in a particular way. We may decide we want to do something about it for that reason or for other reasons. My rule of thumb in the last 5 years is that if I can't get it into PLDI, I stick it into OOPSLA because they've got a bigger page limit. OOPSLA will give you 20 pages, and PLDI will give you 11 or 12 or 13. So that's one thing that has happened, and that has the result of pushing papers in OOPSLA that maybe otherwise don't belong there. So these are things we need to watch out for and study, but I'm not trying to make value judgments about what has happened. I'm just trying to observe cause and effect. Questions?
Just before that, we have to thank Guy for coming.
Thanks for coming. Thank you. Thank you.